All right. Anybody? Hope everybody's okay. So I thought we'd start off with just a little bit of a, let me just review something that I just want to make sure that everybody understands. So if we have a plus b quantity squared, what's the answer to that? What's a plus b quantity squared? Can anybody just tell it to me? Yes, Olivia?
A squared plus b squared plus ab.
A squared plus b squared plus ab.
2ab?
2ab. 2ab. Yeah. So let me just make sure that you guys understand something like this. So there's a couple ways you can think about it. One is, like we said before, using the distributive property, right? You remember the distributive property, it says that if you take something times a sum, right, then that's the same thing as A times B plus A times C, right? And you can think of that in terms of area, right? Probably the easiest way is to think of that as in terms of area, right? If I have A and I'm multiplying it by a length B plus C, right? Then this thing is A, B plus C, right? So this length is A, this length is B plus C, then the area is going to be A times B plus C, right? But you can also think of that as, right, A is B, and let's say that B is this length, and C is this length, right? So, and you see that that's the same thing as AB, right? This area is AB, and this area is AC. Right? So the distributive property is just a statement about area, right? That A times the quantity B plus C is the same area that you get when you get A times B and add it on to A times C, right? So similarly, right, you could write this thing as a, if you want, you could write this thing as a square, not a square, but some sort of rectangle. Right? You say, okay, you've got this length is A, this length is B, right? This length is A, this length is B, right? And A plus B, so this length is A plus B, right? This length is also A plus B, right? And when you multiply A plus B times A plus B, what do you get? Well, you get this total area. Well, the total area, what's this area here? A squared, right? What's this area here? B squared, right? And what are these guys? AB and BA or AB, it's the same thing, of course, right? And so you see that you get A squared, right? A squared plus 2AB plus B squared, right? So that way I hope you never forget, right, what this formula is, because hopefully you don't try to remember it, but you understand it, right? That you understand it as, this is a statement about areas, right? So you can do it. You can think about it pictorially, or you can think about it, algebraically, right? So you could say, well, using the distributive property, this is something times a sum, right? So I'm going to have this is my A, and this is my B plus C, right? So I'm going to have the first thing times the sum, whoops. So the first thing times A, and the first thing times B, right? I get my AB times AB plus AC, right? And then right? So I'm just using the distributive property, right? And then I use the distributive property again. I get A squared plus BA. Here I get AB plus B squared, right? And so you get A squared plus 2AB plus B squared, right? So if you want, some people like to think about things according to rules and algebra, so algebraic rules, right? Other people like to think about things geometrically. I prefer geometrically myself, but whatever you like. I always say that there are different types of mathematicians. Not every mathematician likes every kind of mathematics, right? There's sort of three vastly different personality types, I always say. There are the analysts, the algebraists, and the geometers, and this is just my idea based on the mathematicians that I've met, mainly in graduate school. And so my impression was that the algebraists were all these sort of cold people who'd come in and they'd be like, so you have this definition of a field, and then they'd start writing down long strings of formulas and stuff like that. And the geometers were these sort of wild-eyed people. They'd come in and they'd say, so then they draw something like this and they say, and this has this kind of property. Don't you see it? And they sort of they're like hypnotists or something. Like always like looking at you as if they could persuade you what was in their head was in your head. I found the geometers to be really interesting. And then there's the analysts, and these are like more normal people. I'm an analyst. So I lean towards more towards this side than that side. I always enjoyed analysis and algebra. I didn't really get the hang of geometry. Anyway, so just another example, quick. A minus b squared, well, what's that going to be? Same sort of picture, right? You've got a and you've got minus b, right? So you've got a number a and you've got a number minus b. Okay, a and minus b. So you get a squared. Here you get a times minus b. Here you get the minus b times a. And here you get minus b times minus b, which is b squared, right? And so you end up with a squared minus 2ab plus b squared. Okay. So multiplication is areas, right? Think of multiplication always as areas, right? And you'll never go wrong with this kind of problem. Okay, and we're going to need that today. I don't believe in hypnotism as a way of teaching. Okay, which is good because I don't make eye contact anyway. Okay. Okay. So today we're going into section 1.7. This is about symmetry. Right, and symmetry is something that human beings have a sense of kind of intuitively, right? You see something and it's pleasing. It's often pleasing to you if it's symmetric. Like people say that human faces are pleasing if they're symmetric. That always seems strange to me. Like if you took just any face and then reflected it, would that be a pleasing face? Anyway, human beings have a sense of symmetry, and we want to think about how symmetry. We want to ask, how is symmetry reflected? How is maybe the symmetry of a graph reflected in its equation? Right? How is the symmetry of a graph reflected in its equation? Right? We've been talking about graphs, graphs of two variable equations. So I have some pictures. So like you could have something like this, right? So I'm gonna have something like a circle, right? It's got eyes, it's got a mouth. Okay, right. That has some symmetry, right? You see that it's got this like left-right symmetry. Right, I'm gonna turn it sideways. So you've got this kind of thing, and you see this got this up-down symmetry, right? If you reflect it this way, then it's you get the same thing, right? And another one, the eye is up here, this eye is down here, and the mouth is here, mouth is here. Okay, so this has another kind of symmetry. This is kind of like a nightmare that I had when I was a child, of the rearranger. So there was this guy, and it was a regular occurrence in my dreams. This guy would come around and rearrange your face. Like he would take your mouth and stick it up here, and then take your eye and stick it up. It's pretty horrifying. But anyway, I don't have that dream anymore, thankfully. Yeah. Okay. In any case, all of these things you sort of feel have a symmetry. This one is called, symmetric about symmetric about the x-axis, the y-axis. Symmetric about the y-axis, right? So we give these things names. Symmetric about the y-axis because you can reflect it across the y-axis, right? Symmetric about the x-axis. And then this last one is called symmetric about the origin. That one always didn't make much sense to me, but what it means is that if you reflect the graph this way and then this way, you get the same graph. So you reflect it across the y-axis and the x, and then across the x-axis, or vice versa. X-axis and then y-axis, and you get the same thing, right? So here you see if you reflect it, you get the same thing. You reflect it, you get the same thing, right? So this is actually leads you to some idea in algebra called the idea of a group. You think about how many different ways can you take an object and then reflect it, and still get the same thing. Anyway, that's you don't need to know that. Okay, so right, so we've got names for this. So we've got sort of like terminology for this, right? Symmetry about x, x, y, and origin. As a statement about the graphs themselves, you could say that the first one, so let me just call these guys, I'll call this thing 1, 2, and 3, right? 1, 2, 3. A way of saying it a bit more mathematically is to say that a point lies on the graph if and only if this point, negative xy, lies on the graph. Okay, so the graph G is symmetric about the y-axis. It's symmetric about the y-axis if whenever you have a point on the graph, whenever you have a point xy on the graph, the point negative xy is also on the graph, right? You guys see that? I hope you guys understand that, right? So like, if I take this point on the graph, this point is xy, and you notice that the corresponding point, negative xy, is also on the graph, right? This point here, if this point is, a comma b, then this point, negative a comma b, is also on the graph, right? It has this property that every point with coordinates xy corresponds to a point negative xy on the other side, right? So it's got this symmetry. Okay, right? What should I rate here for symmetric about the x-axis? Take 10 seconds and fill in what these two blanks should say. How do you describe symmetry about the x-axis using this kind of notation? Okay, turn to somebody nearby and talk with them. Okay, would somebody like to say what they think? Stella, yes. This one?
So for the second one, I wrote, point xy is an element of G if x comma negative y is an element of G.
Exactly. a point lies on the graph if and only if its reflection across the reflection across the x-axis lies on the graph. What about this one? A point lies on the graph if and only if. Anybody? Lisa? Negative x, negative y lies on G. Right. And you guys see that, I hope, right? You see that if this point xy here, right, you reflect it, first you reflect it to here, this would be x negative y, and then you reflect it again, this would be negative x negative y, right? Or you could go across this way and then down, whichever, doesn't make any difference. You reflect in this way and then that way is the same as reflecting this way and then that way. Okay. Okay. Is this clear? So this is one way of describing symmetry mathematically, right? Symmetry of the graph means that that the points all satisfy these. The point, a point lies on the graph if and only if its reflection across the y-axis lies on the graph that's symmetric about the y-axis, and so on and so forth. In terms of equations, so this is sort of like in terms of the graph. If we want to talk about in terms of the equation, I think it's what this is saying is that this is a solution of the equation if and only if this is a solution of the equation, right? Remember what it means to be on the graph. It means you're a solution, right? So in terms of the equation, what this is saying is that this is a solution if and only if this is a solution. So like, in terms of the graph, you see that replacing x by negative x results in the same equation. Okay, so let me give you an example. Let me give you an example of that. Parabolas. Right. So the parabola of y equals x squared has a symmetry about the y-axis, and you notice that when you replace x by negative x, right? If I take this equation and I replace all the x's by negative x's, I get the same equation, right? I get the same equation. This is the same equation, right? Which tells you that whenever xy satisfies it, negative xy is going to satisfy it because it's the same equation. Okay. Okay. So, right. What do you think the remaining boxes are going to be? What do you think? This one, take a few seconds and write something down, please. Okay, turn to somebody nearby and talk with them. Okay, what are we going to say here? Somebody? Replacing y by negative y doesn't change the equation, right? Yields the same equation. And For the last one, anybody want to say it? Maybe it's too straightforward. Zoe, go ahead.
X, y with negative x, negative one.
So x replacing x and y by negative x and negative y respectively. Yields the same equation. Okay, so let me, you can make, it's, for the second one, it's pretty straightforward. You could easily come up with, x equals y squared, right? A parabola going this way, right? And you see that if you replace y by negative y, it doesn't change, right? Right? You could have something more complicated, like this plus 3y to the fourth, say. I don't know what the graph looks like, but it's probably something kind of similar to that, right? You see that this one would also be symmetric about the x-axis, right? Because whenever, if xy satisfies it, right? If you have some point x naught, y naught, and you put it in and it satisfies it. So suppose, right, if this is a solution, that means that x naught equals y naught squared plus 3 y naught to the fourth, right? But then you notice that x naught negative y naught is also a solution, right? Because if you put in x naught negative y naught, you're going to get x naught negative y naught squared plus 3 negative y naught to the fourth. But this thing is the same thing as that thing. And so, right, if these two are equal, then these two are certainly equal, right? If these two are equal, then these two are equal because this is that, right? So if this works in there, then this is going to work in there. So it's got the symmetry. Okay. Let me just put up some examples. So, for example, if I have something like x equals y squared minus 1, what kind of symmetry does it have?
X squared, or x-axis.
X-axis symmetry, right? If you replace y by negative y, the equation doesn't change, right? Right? If I had something like this, what would you say?
Origin. Symmetry with origin.
Yep, yep, right, because you can replace x, if you replace x and y by negative x and negative y, the equation doesn't change, right? If I have something like this, what would it be? Y-axis, yep, right. So you replace y, if you replace x by negative x, you see that, right? So this is saying if you have your function, if you have your point x, y, it lies on the graph, negative x comma y is going to also satisfy this equation, right? So it's symmetric about the y-axis. Here's one. Take 30 seconds and think about it. Here's an equation. The absolute value of x plus y equals 2. What kind of symmetry does that have? Or if you want to try something a little bit easier first. You could think about that one first, and then the other. Talk with somebody, please. I'll give you half a minute or a minute to talk with somebody. Okay, what kind of symmetry does this graph have? Anybody want to say? Y-axis, right? Because if you replace x by negative x, you get the same thing, right? Because absolute value of negative x is the same thing as the absolute value of x, right? So if I replace this by negative x, I still get the same equation, right? So yeah, so you say, well, look, equals this, so it's the same equation. Okay. What about and if you drew it on the plane, that would be everything whose x value is 2 or negative 2, right? 1, 2. So it would look like this. The solution set would be these two lines here, right? So you can sort of see, graphically that it is symmetric about the y-axis. Okay. What about the last one? Absolute value of x plus y equals 2.
Would it be symmetric about the origin?
Symmetric about the origin. How come? Why do you think that?
Because if you replaced x with negative x and y with negative y, it would still be the same equation.
Yes.
Because they're equidistant from 0, right?
What's the equidistance from 0?
Well, like, just talking about like what absolute value is. Yeah.
Okay, yeah. So maybe one way to see this algebraically, so I think you understand it kind of intuitively. One way to see that algebraically is to say, well, look, this thing is just negative 1 times x plus y, right? Right, and we just noticed that remember the absolute value of negative something is the same thing as the absolute value of that something, right? Right. If you don't like that, you can think of it as, well, this is the absolute value of a product, right? And what's the absolute value of a product? The absolute value of a product AB is, anybody remember this rule? Fern? Exactly, right? Is the product of the absolute values, right? The absolute value of a product is the product of the absolute values. And so we get the absolute value of negative 1 times the absolute value of x plus y. Right? But the absolute value of negative 1 is just 1, and so we're left with the absolute value of x plus y. So we get the same thing. Okay. Geometrically, anybody know what this looks like? It'll actually turn out to be a box. It'll look like this. Where these are all, this is 2, this is 2. This is square, sideways. Okay. Okay, that's all I want to say about symmetry. That's all I want to change the subject a little bit. So let's talk about circles, which is kind of a natural thing to talk about when you're talking about symmetry. So remember what a circle is, right? A circle is is the set of points, or maybe I should say a set of points, equidistant from some central point. Okay, and when we say it's equidistant, let's say that the distance is called r, right? Which stands, of course, for radius, right? So it's all points, right? It's all set of points equidistant from some central point, x naught, y naught. Right? That's what a circle, that's the definition of a circle. Okay. So, if we write that in mathematical language, right, that's saying that it's the circle is all xy such that the distance between xy and x naught, y naught is some fixed number r. Right? Just rewriting the same thing in something pretty close to English. Right? It's a set of all points xy in the plane such that, and this such that, remember, is basically with the property that all points in the plane with the property that their distances from this central guy is equal to r. Okay. If we use the distance formula, we can write that as, well, this is going to be x minus x naught squared, the distance, y minus y naught squared equals r. Okay. And because we're dealing with positive numbers, it doesn't change anything if we square this. We get x minus x naught squared plus y minus y naught squared equals r. So this is the formula of the circle that I hope you're familiar with. Right? So it's just a mathematical translation of this English definition. Right? So, if you see an equation that looks like this, x plus 4 quantity squared plus y minus 3 quantity squared equals 1, maybe let's say equals 9, then what circle is that describing? Oops, this should be an r squared. Sorry. What circle is this describing? What would be the center of this circle? Amy? Negative 4, comma 3, right, is the center. And then what's the radius? 3, right? Radius 3. Right? Right. In this case, the circle has been written in a way that makes it really evident, right, what this is saying. Right? This is, you can look at it and just say, oh, look, this says that the square of the distance to negative 4, 3 is 9, right? Because this thing is the distance formula squared, right? So, yeah. Often, it's not gonna be so explicitly given to you. It'll be disguised, right? So they'll give you something like, so this is, it's not really, it's more like an obfuscation. Right, when somebody takes something simple and then like messes it up to make it seem confusing, but it's actually simple. But anyway, so here's the example. Like, suppose you have something like this: 9x squared plus 54x plus 9y squared minus 6y plus 64 equals 0. Okay. So it doesn't seem like it's a circle, but if you had written this out, if they had spelled this out, right, this would have been x squared plus 8x plus y squared minus 6y plus 25 plus 16 equals 0, right? So they could have done the same thing with this one, right? It's just the same sort of thing. You can go from here to here. You can go from the easy one to the obfuscated one easily, but coming backwards is a little bit tricky. Okay. To come backwards, you need to use the algebraic trick of completing the square. Okay, so let me just remind people what completing the square is, in case you've never seen it or you've forgotten it. This is an algebraic trick. So completing the square is going to allow us to go from the confused one back to the simple one. Okay. It's a way of basically reveal symmetry. completing the square. So here's the idea. So here's the idea. Suppose you have x squared plus ax. Okay. You have x squared plus ax. You want something like a square. You want to express this as a square somehow. Okay. And what I mean by that is that you would like to express it as something where you've got something up here and something up here. Okay. Okay. And x squared plus ax should be somewhere here. Okay. So let me show you what I'm talking about. Okay. So here's the idea. What you do is you think, well, look, if I have x plus a over 2, and I take it and multiply it by x. So let's draw this kind of picture again. Suppose I've got x and a over 2 and x and a over 2. Okay. Then what is this going to be? What's this area here? What's x times x? X squared, right? What's this going to be? A over 2 x. And what's this going to be? A over 2 times x again, right? Okay, now just look at these things I've put up now. I've got x squared and I've got a over 2x and a over 2x, right? Right? That's the same thing as this, right? That is what this thing here is this total thing here. Well, this total thing here is my x squared plus ax. Okay. Yes?
How did you get a over 2?
Just so that this would work out.
Oh.
Yeah, I wanted to make something with x squared plus ax, and so I chose a over 2 because I knew that would give me a over 2x here and a over 2x here, and those two add up to the ax that I want. Okay, so it's sort of like, yeah. Okay. Okay. So, right. So what you see is that this thing is almost a square, right? Right. What am I missing? What do I need to complete the square? Well, what's the area of this thing? What's the area of this thing? Well, anybody?
A over 2 squared.
A over 2 quantity squared, right? A over 2 quantity squared, right? So if I had this, right? So what you see is that if I had an extra a over 2 squared, that is a squared over 4, then I'd actually have a square. A square, namely, it would be x plus a over 2 quantity squared. Okay, so here's the idea. So here's the trick. If I have x squared plus ax, just add on a cleverly chosen 0. Okay, so I've got this x squared plus ax, and I'm going to add on 0. My 0 is going to look like this. This thing squared minus this thing squared. Okay. Why did I do that? Because now this thing is a completed square. Right? Now I've got that square, right? I can express this thing, right? I was missing this a root 2 quantity squared. Now that I just throw it in, and I get this thing expressed as a square. Okay, yeah, I have to subtract this thing off, but at least I got this thing expressed as a square. Okay, I'm going to say that in a slightly different way. Okay, so in case you didn't like that, I'm going to say it in a different way. It's not that different, so maybe you'll still dislike it. Okay, so it's actually the same way. So here's I don't know if this is alternate viewpoint or exactly the same viewpoint. So whenever you have x squared plus ax, x squared plus ax, you can rewrite it as x plus a root 2 quantity squared minus a root 2 squared. Right? Why? Well, let's multiply this thing out. What happens when you multiply this thing out? Who can tell me what this sum quantity squared is? What do you get when you square a sum? You're going to get this guy squared, right? This guy squared. You're going to get this guy times 2, right? So you get 2 and 2x, and you get the last guy squared, a root 2 squared, right? So this thing here is this, right? Oh, nope. Sorry, I forgot about this thing. Okay. And you see that what happens is these guys cancel off, the 2's cancel off, and you get x squared plus ax. It's the same thing. I don't know if that was any better. But in any case, the trick is that the thing is that is this, right? Whenever you see something like this, you can express it as you can slide in this sort of term, which is a completed square. Okay. You do need to throw in something else because when you completed that square, you added something, right? So you need to subtract that off because you can't just put in numbers whenever. You can't just add things whenever you feel like it, right? But when you do get your completed square. Okay. Let me do an example or two, and hopefully that will make it clear. Okay. So here's a simple example. So x squared plus 2x. Okay. So this is my x squared plus ax, and you see that okay, I can express this as x plus a over 2 quantity squared minus a over 2 quantity squared. Right? If I work it out, you see that it works out, right? You get x squared plus 2x plus 1 minus 1, right? Which is indeed what we started off with. Okay. So, right? So you've taken your x squared plus ax, and you express it as x plus a over 2 quantity squared minus a over 2 quantity squared. Right? What if I had something like this? X squared plus 8x. Take 30 seconds and express this as a completed square plus the correction term. turn to your partner and talk.
Oh, this is
Okay, what are we gonna put in here? X plus what squared? 4, right? Because you need half of this thing, right? Because when you multiply this out, you're gonna get twice, 4 times x, right? So you're gonna need half of this, and then you need to subtract off. What do you need to subtract off? 16, right? That 4 squared, right? Okay. What about something like this? X squared minus 8x. Well, you're going to have x plus your a over 2. Now your a is -8, right? So we need a -4 here, right? And that makes sense because, right, when you multiply this out, you're going to get x squared plus twice -4 times x. That will give you your -8x, right? So if you understand, this formula, x squared minus 2a x plus a squared, then you should understand it should be pretty intuitive to you what number to choose, right? And then we need to subtract off that -4 quantity squared. Oops, missing a square. Okay. Let me show you, so what's the point here is that this reveals some symmetries. Let me show you, I'll talk a little bit more about that next time, but let me just show you how this is applied in terms of the exercises. So here is some equation, x squared plus y squared plus 8x minus 2y minus 8 equals 0. Okay. And you want to recognize this as a circle. You want to figure out the center and the radius. Okay. So you say, okay, well, this is x squared plus 8x. This is y squared minus 2y. And I'm going to move the 8 to the other side. It doesn't matter. I could leave it, but I'm going to move it to the other side. Okay. So it's not really evident, right, what the center is, but we use the completing the square to reveal symmetry, right? So we say, okay, let's complete the square for this guy. We've just done it, actually. So it's going to be x plus 4 quantity squared minus 4 squared, right? What about for this one? This is going to be y plus -1 squared, right? And then minus -1 squared. So you do the completing the square on each of these parts, right? Do completing the square on each of these parts, and lo and behold, what do you get? You get x plus 4 quantity squared. I'm going to move all the constants to the right side. So I have a 16 on the right side. I also have an additional 1, and I have a 25 on the right side. So it's 17. I move 17 to the right side. I get 25. Right, and now you can read it off easily, right? It's centered at -4, 1, and it has a radius of 5. Okay. In the homework, it'll be a slightly more complicated. They'll have something like this, like 3x squared plus 3y squared plus 5x minus 4y equals 1. Okay. The thing to do at this point would be to just divide by 3. You're allowed to multiply an equation by a non-zero number, right? So let's multiply on both sides by 1/3. right? And then you're in the same position as before, and you use completing the square again. So that's, you know, that's just a almost a useless obfuscation. Okay, but what's the point of all this is that you're taking something where the symmetries are not evident, and then you're using this technique to make the symmetries evident. That's really the point of completing the square. You're saying, oh look, this thing is symmetric. This thing is x-symmetric about -4, right? Right. This thing is I'm sorry, about 4, right? Right. This thing is symmetric about -1, right? Anyway, I'll say a little bit more about it next time. But, okay, that's it for today. We finished 1.7, and the homework will be everything on the syllabus for 1.7. So I'll send out a note later.